record to the cloud. All right, welcome to the last day, everybody. We made it. The semester is over. I mean, you know, except for final exams and all that good stuff. So you guys are hopefully still working on your final projects, but this will be our last lecture. The topic I wanted to cover today, and it's, 10 pounds of flour in a 5-pound bag, is a little more sort of conceptual, about mirror symmetry. Where does it come from? How does that get expressed mathematically? This is still a topic that is very active research. So even if I were a perfect expert and I had all the time in the world, I don't think I could give you the fullest answer we would like, but I'm going to do my best. So what we talked about last time was sort of how mirror symmetry entered the consciousness of mathematicians. Basically, physicists wrote a paper that said, hey, we have this mirror symmetry prediction. It tells us how many curves of a given degree there are in a quintic. And mathematicians said, oh, that's crazy. How did you know that? That's a really hard problem. And then they got interested in, okay, well, how did the physicists figure this out? How does this get expressed mathematically? So sort of the thing we talked about before was kind of the relationship between the number of rational curves with a given homology class, and you can expand that to curves of higher genus, meeting certain incidence conditions inside one Calabi-Yau manifold M. And on the dual side, something about the complex geometry of M, which is often expressed in terms of period integrals. All right. Well, something I didn't address, which is kind of the obvious question, is how do you actually get this M dual from M? What is like the mathematical relationship between them somehow? This is a phenomenon I've encountered many places in dualities in physics. The physicists say, well, you do this duality, another thing comes out, and you're like, okay, there should be some mathematics behind that. What is it? In the previous class, when sort of mathematicians were first introduced to this, it was just kind of like, well, in this case, here's the answer. And maybe if you looked in some other case, they could tell you the answer in that other case, but it was sort of a case-by-case thing. And a lot of it was just kind of observing, doing the calculation on both sides, for example, of the Hodge numbers, and seeing that they matched up. Now, obviously, that's not a satisfactory approach. We want some more conceptual explanation of where this mirror manifold comes from. So I think the first kind of major advance, we're now getting into the early to mid 90s. A lot of the exciting action in this area happened around then. I think this was in about 94. Was a work of Batirev that explained sort of one big interesting class of mirror dual pairs in terms of toric manifolds. So I wanted to discuss this in part because it brings back things we talked about earlier in the course, where we can look at the geometry of these Delson polytopes. So consider a Delson polytope. And before, remember, with Delson polytopes, we only sort of considered for each vertex, what are kind of the slopes, or more generally kind of the directions that the edges coming out of each vertex are. Those had a sort of integrality property that they needed to have, but we didn't assume anything about the distances along the edges being integral. So I'm going to assume something stronger. I'm going to assume that my Delson polytope has vertices in Zn. And I didn't write this. The sort of significance of this condition is that's basically what you need to make sure that the symplectic form is an integral cohomology class, which in particular you're going to want. I tend to think about this stuff in terms of algebraic geometry, in which case I'm saying, oh, well, those are the symplectic forms that can come as pullback of the Fubini-Studi form. Fubini-Studi form is corresponds to an integral cohomology class on Pn. So any symplectic form that's the pullback of Fubini-Studi under some inclusion of Kähler manifolds which would have to be projective varieties, into Pn comes from, it gives you an integral form and vice versa. All right, so, and for reasons that will be clear in the moment, I also want this to be placed so that the origin sits inside the polytope. And the reason is, then I get a nice definition of this guy called the polar. So the polar of a given polytope is all the elements of Rn, which you should think of as the dual Rn. It's the dual space, such that when I take the inner product with every element of my original polytope, I get something larger than -1. So every element of the polar gives me a linear inequality that all the elements of my original polytope satisfy. And every such equation corresponds to a point in the polar. So in particular, facets of my original polytope, so those are faces which are one dimension lower than the whole polytope, so kind of the maximal dimensional faces on the boundary. Well, each one of those is defined by a single linear equation. That gives me a point of the polar, which you can work out is a vertex. So the polar is a polytope, and each vertex corresponds to a facet of delta. And so the reason to have the origin in the middle has to do with exactly what the inequalities you satisfy will be. So somehow, if you didn't have the origin in the middle, you wouldn't be able to write every linear inequality satisfied by the polytope in this form. All right, so for example, if my polytope is in R, well, then it's a interval of the form A to B, and its polar is the interval from -1/B to -1/A. And so it's important that A and B have opposite signs so that everything stays in the right order. Similarly, if I take a square, so, easy example of a polytope. So the way to find the polar, is every facet has an inward pointing normal vector. And that inward pointing normal vector, when it's normalized so that it has inner product -1 with everything along that hyperplane, gives me a vertex of the polar. So in this case, right, this guy corresponds to this vertex, this guy corresponds to this vertex, and this guy corresponds to this vertex, this guy corresponds to this vertex. So I'm taking this normal vector and thinking of that as an actual vector in Rn. All right, so we call a polytope Fano if its polar also has all vertices at lattice points. So for example, if I take the interval from -1 to 1, well, if you look at that formula I had up above, that's its own polar. If I look at this square, then it's Fano, its polar has vertices at integral points, but this is worth noting here, its polar is not going to be Delson. So this is a kind of common phenomenon that you put in a Delson polytope, even if its polar has all its vertices on integral points, it still won't be Delson. And I'll just mention the reason it's not Delson, right, is when I look at any one of these vertices, the two edges coming out, they'll be like 1, 1, and 1 minus 1, and they won't span Z mod NZ, Z to the N, sorry, because they won't be linearly independent mod 2. All right, and one more kind of interesting example I can take. So remember, I need to make sure that the origin is in the center. So in this guy, this is the origin, and I'm taking a triangle that goes around the origin. So its vertices are -1, -1, 2, -1, and -1, 2. All right, and that guy is phono. Again, if I want to find its polar, right, I should look at the normal vectors to the faces, so the facets, I should say. So that guy corresponds to this vertex. Oops. This guy corresponds to this vertex. This guy corresponds to this vertex. All right, and again, this polar is not Delson. You'll see there's an issue if you consider things mod 3. Right, so a set of integral vectors are a basis of Zn if they're a basis mod every prime. And so sometimes it's sort of easier to spot things which aren't bases of Zn by reducing mod a prime and seeing a problem. So remember, we're talking about symplectic geometry here. So I'm interested in these Delsons giving me toric manifolds, toric symplectic manifolds. So for example, here I'm getting P1, here I'm getting P1 times P1, and here I'm getting CP2. And I'll just mention here, note, I'm getting all of these manifolds with specific symplectic forms that maybe aren't the obvious ones. So for example, this is CP2, but it's not CP2 with the Fubini-Studi form. It's CP2 with 3 times the Fubini-Studi form. And we'll see what's happening in a moment there. All right, are there any questions about this definition? So this is just sort of combinatorics, but it'll tell us something interesting about these symplectic toric manifolds.
Are we considering these polytopes as having as being like the moment map from a torus action, or are we just?
Yes. So
okay.
there's a unique symplectic toric manifold that this is the moment map image of. So here it's P1, here it's P1, here's its CP2. And what's happening, I'll just mention these guys that aren't Delson, right? We talked about what happens if you have a polytope which is simple but not Delson. So it looks like a Delson polytope over the rational numbers. So at every point, it looks like a corner of an orthant, but you can't move it to a corner of an orthant by an invertible transformation over the integers, only over the rational numbers. Then what you get is an orbifold. So for example, here, this polar, this isn't Delson. It corresponds to the orbifold CP2 mod the action of Z3. Where I can explain later what the Z3 action is, but there's sort of only one Z3 action on CP2 by diagonal matrices with determinant 1, and that's the unique one.
And is this polar, is there some analog of the moment map for this sort of singular scenario?
Well, there's a symplectic orbifold. So there's a notion of what it means to have a symplectic form on an orbifold, because orbifolds have perfectly fine tangent spaces, and you just do everything out exactly the same way. So if you go back and look at the construction we did, you just do exactly the same thing. So it's the story of you take your polytope, you write it as taking the negative orthant in some higher dimensional space and slicing that with an affine subspace. And the affine subspace you choose tells you a torus you should reduce by. And in the case where your polytope is simple but not Delson, what's going to happen is the action of that torus on the moment map level is locally free, but not free. There will be finite stabilizers at some point, and so the quotient will be an orbifold. Right, like what's happening here is I have a torus acting, you know, I can write this guy as a torus quotient, and then at these vertices, my torus doesn't act freely. There's a subgroup of order 3 that acts trivially. In this case, this is going to be a weighted projective space. I haven't done this example in detail, so I'll need to think about it. But you know, it's going to be I would need to think about it what it actually is, but I'm sure it's actually something pretty simple in this case. But yeah, so it's just that it's an orbifold, but orbifolds have tangent spaces. It's just like they get modded out by finite groups at some points. But there's a perfectly good symplectic form that, you know, and it just comes from the symplectic reduction, right? You just do exactly the same thing you did to construct the moment map on a symplectic reduction by free action, and you just say, oh, there's actually a finite group stabilizing things here, so I'm going to get an orbifold point. All right, yeah. So that's we can talk more about that some other time. But I think I only have so much time, so I should probably keep going. Okay, so what's the significance of this Fano property geometrically? Well, Fano is actually the name of a geometric property that a complex manifold could have. So if delta is Delson and has this Fano property, so it has integral vertices and its polar has integral vertices as well, then the corresponding toric manifold is a smooth projective variety. And the symplectic form, coming from the way we've realized it this way, is the Fubini-Studi form of the pullback. And I sort of tried to say this in the most symplectic way possible, but let me just say, for the sake of people who actually know algebraic geometry, I've embedded it in projective space using the anti-canonical bundle. So Fano, being Fano, means that the anti-canonical bundle is ample, and it gives you an embedding into projective space. So the way to say that symplectically is that the symplectic form is the curvature of a connection on the anti-canonical bundle. All right, what's the significance of that? Well, it means that if I look at this projective embedding and then I intersect with any hyperplane in projective space, the submanifold or subvariety of my toric manifold will be Calabi-Yau. So this is just a calculation with the Chern classes. Because I'm using the anti-canonical bundle to do my embedding, a hyperplane section is automatically Calabi-Yau. So every time I have one of these Fano toric varieties, I automatically get a Calabi-Yau. So for example, this one that I had that's CP2, well, the Calabi-Yau I get is any elliptic curve in CP2, every elliptic curve in CP2. So the significance of it being 3 times the Fubini-Studi form is that hyperplane section is going to be the 0 of a degree 3 polynomial, or section of O of 3 on projective space. So yeah, the zeros of a degree 3 homogeneous polynomial. Now you can see that here, in that it's 3 times the size of the usual simplex. And indeed, those of you who know your CP2 know that the canonical bundle is O of minus 3. So the anti-canonical bundle is O of 3. That gives you your embedding. And more generally, you can always, the CPN is always Fano. the corresponding polytope is you take the usual version of the polytope for CPN, you multiply it by n+1, so it gets n+1 bigger. That's the right thing for the anti-canonical bundle on CN. And then you subtract -1 from all the coordinates, so you center it. It's worth looking at this picture here for CP2 because it's a lot harder to draw for CP4, which is the relevant one for 3D Calabi-Yau. So this is Fano. I've written out the vertices of its polar. So its polar has integral vertices, but as we saw in the example of CP2, it's not Delson anymore. So it corresponds to CPN mod a finite subgroup. And it's always the diagonal matrices with determinant 1 whose entries are n plus first roots of unity. I was going to give myself a tiny bit more space here. So sorry, I was just going to say that in this case, the Calabi-Yau that results is degree n+1 hypersurface in CPN, and it's degree n+1 because I scaled up the polytope by multiplying it by n+1. So I multiplied my symplectic form by n+1. And so to get that as the pullback of Fubini-Studi, I have to use the n+1 Upal embedding of CPN into a much bigger projective space. And so a hyperplane section is just the vanishing set of a degree n+1 polynomial. So that's always kind of the easiest Calabi-Yaus to cook up, or just any smooth n+1 degree hypersurface in CPN. So the toric case is a big generalization of this. And the sort of proposal theorem, right? It's hard to call it a theorem because we don't know the kind of full perfect statement of a mirror symmetry, but it's kind of a theorem at this point. If you start with a Delson and Fano polytope, then it has a Calabi-Yau hyperplane section inside of it, coming from this anti-canonical embedding. And that is mirror dual to, well, I take the polar, that's going to correspond to a singular toric variety. And I take also a generic hyperplane section of that guy. That's going to be singular, so I'm going to take a Crepin resolution of it. And that will give me the mirror Calabi-Yau. I should say here, there can be some issues with whether that Crepin resolution exists, but if it does, then it gives the mirror to this toric variety, or this hypersurface inside a toric variety. All right, so this at least kind of gives us a bigger framework and a lot of interesting examples. And we're able to check things about these examples because toric manifolds are so nice and so easy to understand. The algebraic geometry behind them is relatively simple. You can express stuff in combinatorial terms. So Baturev, a little bit later, proved the mirror symmetry of the Hodge diamonds. And even if there isn't a Crepin resolution, there's sort of a way of defining what are called stringy Hodge numbers, which are sort of what would be the Hodge numbers of a resolution if the resolution existed. And you get exactly the symmetry of the Hodge diamond. And then later work of Giventhal actually showed that the quantum cohomology matched the B side chiral ring as well. All right, so this is one really powerful idea in mirror symmetry. This is kind of the first time clinicians really got their hands on it as a sort of concrete thing where you could actually do calculations and find lots of mirrors. I should say this idea has been refined a lot. This is just kind of the first version of it. So it's been extended to varieties with bigger codimension inside toric varieties. And it eventually led to this, what's called Gross-Siebert program, where you take a Calabi-Yau and you degenerate it to something toric, and then you can apply this to the Batirev duality to the degeneration and then try to undegenerate. And this has lots of interesting connections to tropical geometry, but it's definitely not something I'm an expert in. Right, are there any questions about this story? Okay, great. So that's cool, but it doesn't actually tell us anything about how to construct M dual in general, right? It's a little bit dissatisfying. It's one of these results that is very interesting, but it sort of keeps you thinking, okay, but what's the actual thing underlying this? There should be some more basic principle. And I think we at least have a sense of this more basic principle, though it's quite hard to implement in practice. So a little while after Batirev's result, this was in about 96, there was a conjecture, again, conjecture / proposal / idea of Strominger, Yau, and Zaslow, that if you have a mirror pair of Calabi-Yaus, they should actually be fibrations over a common base. That there should be some base manifold B, a map from M to B, a map from M dual to B. And the fibers of this map should be Lagrangian. They should even be special Lagrangian. I don't think I want to worry about what that means. And generically, the pre-images, I didn't do a very good job of saying pre-image here. And for any point in the base, I have two pre-images. And for a generic point in the base, I should be getting dual tori. I should just mention dual torus in this case means if I write my torus as Rn mod a lattice, and usually I want to have a fixed flat metric on my torus, which kind of uniquely determines lambda up to isometry, then there's a dual lattice to lambda inside Rn. So this is a generalization of this idea of you have a circle and you take the reciprocal of the radius of the circle. That does, so in general, if you take the dual torus, its volume will be the reciprocal of the original torus. But of course, there's also more interesting stuff about the shape going on here, where, if the geodesics in one torus are short, it'll make the geodesics in the dual large. So there are a lot of issues with making the statement precise. One is, well, it only really makes sense to talk about this dual torus when you have a flat metric. In general, the Calabi-Yau metrics on these tori won't be flat, but they get closer and closer to being flat in what's called the large complex structure limit. So a lot of people will tell you, oh, well, this isn't really a statement about kind of all possible complex structures. It's a statement about kind of the limit, a certain limit point of the complex structures. The other really unfortunate thing about this is this fibration is very much not easy to write down. So in Strominger, Yau, and Zaslow's paper, they sort of explain why such a thing should exist. I think at the time they literally could not construct any interesting examples. So it's very complicated to construct even in the best known examples. So it was several years after SYZ's paper that this was even proven for the quintic in P3, P4. And it took like 3 papers and something like 200 journal pages. So this is not something where it's just like write down a few formulas and there it is. I sort of was trying for a little while to be like, okay, can I write down like actual formulas for this? And I certainly couldn't extract them from the papers on the subject. The very rough idea is actually quite nice though. So you can get a rough sense for how this is supposed to work in the case of the quintic by thinking about a degeneration of the quintic. So one quintic hypersurface, but a very, very singular one, is given by just requiring the product of all the variables to be 0. So if you look at the family of all the quintics, it can degenerate to this guy. So this is a union of 5 CP3s. So this is an example of this sort of Gross-Seibert idea of you can degenerate to a union of toric varieties. And when we apply the moment map to this subvariety, then what it maps to, so remember CP, I'm not going to be able to draw a 4-dimensional simplex, but if I draw a 2-dimensional simplex, so the moment map image of CP2 looks like this. And if I require one of my variables to be 0, that gives me one of these facets. So this singular subvariety, it maps down onto the boundary of the simplex. So here I have 3 CP1s mapping to the boundary of this 2 simplex. It's a little harder to picture, but in 4 dimensions, I have 5 CP3s mapping down to the 5 boundaries of the 4 simplex. Right, so I get this sort of nice map. Well, it's not, the nicest fibration in the world, but generically its fibers are Lagrangian tori. So this singular quintic, it's generically a complex manifold because it's a union of these CP3s, and the preimage of every point in the boundary is Lagrangian torus inside its corresponding CP3. And then you have these singular points, which have a smaller preimage. And so basically, the way you construct the SYZ fibration on the general quintic is to take this fibration on the singular guy and deform it away from the singular point. And all the hard work is showing that you can actually do that that makes sense to deform away from the singular point. There are many other interesting examples of this. For example, the Hitchin fibration. It's a famous example, but it turned out to be quite difficult to implement this in practice. Mirror symmetry is hard. What can you do? All right. Are there any questions? Okay, so where did this proposal come from? It looks, somehow it looks pretty random. It's kind of a nice idea that you're kind of dualizing tori in some family. But it's not obvious from anything we've discussed how you would come up with this idea. And the idea comes from the physics. The kind of physics motivation is that the points in the mirror manifold, certain kinds of boundary conditions for our theory. And so when we go through the mirror correspondence and reverse the A and B twists, so we sort of change some choice somewhere, well, there's still boundary conditions, but they're different kind of boundary condition. and the tori of the SYZ fibration on the mirror manifold equipped with a U1 connection. So I should say here, you can think of the dual torus as Ham from pi1 of the original torus into U1. So as a flat connection on the original torus. So when I look at this SYZ picture, if I have a point M here, maybe it's better to say I have a point P here, well, that maps down to some B. And in M, the way I would see that is I would look at pi inverse of B, and this P defines a U1 connection. On that fiber. All right, so this SYZ is explained by the idea that Lagrangian tori in this case, but just generally Lagrangians with U1 connections should be boundary conditions of the other type. Right, so again, here I've kind of written out what I just said. The points in M dual you can think of as boundary conditions compatible with the B twist of the associated QFT. And then we'll want to think about those in the A sides. Let me say a little bit more about this. I say these points are boundary conditions, the B twist. More generally, the kind of right notion of boundary conditions for this B twist are what are called coherent shapes or complexes of them. This is one of these points where I'm kind of like, oh, probably there's enormous variation amongst students, how much you know about coherent sheaves. But if you're sort of not comfortable with this concept, I think the best way to think about it is holomorphic vector bundles on complex submanifolds of M dual. So coherent sheaves are sort of a generalization of this where you allow the dimension of your vector bundle to jump in a slightly more complicated way than just I have a vector bundle on a subvariety. That's sort of, I have a fiber of some degree on the subvariety and then zero away from the subvariety. So it's kind of a slightly more complicated gluing together of those things. So a point is a special case of this, where you think of that as a subvariety. The single point is a subvariety, and it has a vector bundle, which is just C. And we call that the skyscraper sheaf on P. For some things we want to do, I think I'm okay on time, so we can talk about this. This is something that, you know, it's kind of like, oh, do I want to skip this? Do I not? But I think we'll manage. The way these really manifest in the B boundary conditions is this complexes of vector bundles on the whole variety. But you can always write a vector bundle on a submanifold as a complex of vector bundles on the whole variety. So for example, for the skyscraper sheaf, you can write that as a quotient of the trivial vector bundle. But then in the trivial vector bundle, you have to set all the sections that vanish at your point P to 0. And you need to use a map from another vector bundle in order to do that. And then, well, there'll be some redundancies where you've now set second order functions to 0 twice. And so you need another vector bundle mapping in to kill that. And the calculation I wanted to get to, I mean, this is sort of a long story about the derived category, is that if I compute the X algebra, oh, yes.
So is this actually, so I remember a physicist asking me, why do you want these complexes? You know, why aren't vector bundles good enough for you? And is the point that you want vector bundles, is it the point exactly what you said, that you want not just vector bundles, but vector bundles on subvarieties, and that's why you need complexes?
I think that's a pretty good answer, yeah.
Okay, cool, thank you.
I might be able to give a slightly better answer later, but yeah, one thing is sort of like you want to be able to think about, in this case, it's very useful to be able to think about these points as coherent sheaves. Those will sort of have a very nice identity on the other side in a way that vector bundles on the whole variety won't. All right, so the calculation I was getting to is this resolution is really the right way of computing what the endomorphisms of a coherent sheaf is. Let me not get kind of bogged down into details, but one calculation which will sort of show up later is if you have one of these sheaves that's supported on a point, its self maps, let me say, self X, so that's computing maps, but in this kind of complexy way, gives me an exterior algebra on the tangent space. And where this is coming from is sort of, the grading on this is a homological grading. It has to do with where you are in the complex. So the degree 0 part comes from this guy, the degree 1 part comes from this guy, the degree 2 part comes from this guy. So what this is picking up is sort of, when the degree 1 part is telling you about all the functions you had to set to 0 in order to get just the skyscraper sheaf on the point. So the tangent space, that's all the directions you could go that you had to all set to 0. And then the degree 2 part is what were kind of the redundancies in when you did that. So now you have something that corresponds to a pair of directions, where somehow when you set those to 0, you set something about the combination of them to 0 twice. And then the degree 3 part has to do with like 3 directions and having set those to 0 too many times, etc. I'm happy to talk about this later, but I wanted to emphasize this sort of exterior algebra showing up there, because this is the one interesting homological calculation you might want to do. All right, so this perspective led Kontsevich to make a sort of more mathematical proposal about what it means that you're thinking about B boundary conditions on one side and A boundary conditions on the other. And basically he said, okay, on the B side, I have this coherent sheaf category, which is a well-studied and well-established mathematical thing. And there should be some A side category that corresponds to that. So the coherent sheaf category only depends on the complex structure, as B side things do. So we should have something that only depends on the symplectic structure. And I should say Kontsevich shouldn't get full credit for the idea that this category existed. What he should get credit for is the idea that it connects to this coherent sheaf category through mirror symmetry. So on the B side category, you have complexes of coherent sheaves. There should be some symplectic realization of that, and Lagrangians with U1 valued connections should give you objects in this A side category associated with the symplectic structure. All right, well, this was a conjecture proposal. Again, there's sort of a lot of stuff here where saying the precise version is very hard, but so we know a lot about this category that Kontsevich proposed or wanted us to look at. Again, there had been earlier work. It's usually called the Fukaya category because Fukaya had worked on it earlier. Now, working out all the details of this is still kind of a bit of an ongoing project, but a lot of progress has been made. We understand it a lot better now. So physicists would call this the boundary conditions in the A model on M. Let's say the sort of usual mathematical name is the Fukaya category. And the rough idea is that objects in the Fukaya category are Lagrangians, and I should say with a flat vector bundle. You'll quite often see mathematicians who study the Fukaya category leave this out, but it's going to be important for us because you remember we had points on one side and those corresponded to Lagrangians with a flat connection on them on the other side. And so 2 points in the same SYZ fiber give you the same Lagrangian on the other side, but with different connections. All right. So, with varying levels of precision, the idea is the Hom between 2 Lagrangians should be a complex. So just as we were thinking about complexes of coherent sheaves on the B side, and so Hom between 2 complexes is itself a complex. Here in the Fukaya category, Hom between 2 Lagrangians is going to be a complex. So if you ignore the differential for a moment, a Hom between 2 Lagrangians is an intersection point between them. But then there's a differential that you put into this complex to correct what those intersection points give you. That's a very rough idea. We'll talk about this in a little more detail. Sort of the first example to think about is, what if we take T star of some manifold X and look at X inside there as a Lagrangian? And I'm going to look at Hom of that to itself in the Fukaya category. Hom of that to itself, that's not very good. Seems kind of complicated. In particular, every point is an intersection point. So I don't want to do that, as often happens in intersection theory. I want to deform one of these guys a little bit. So I'm going to deform by a Hamiltonian vector field. And to make my life a little easier, I'm going to get one by taking a generic function on my base manifold and pulling that back to T star. When you take the Hamiltonian vector field of that, you get the vector field on the cotangent bundle, which it points along the fibers because it's constant along the fibers. And it points in the direction of df at that point. So you need to think about this a little bit, but each cotangent fiber, it's a vector space. So tangent vector to it is just an element of that vector space. And you think of df of x as an element of the vector space and then turn that into a tangent vector. So if we evolve x for time 1 under this Hamiltonian vector field, what we get is the graph of the one form df. So we're taking x, we replace it with the graph of an exact one form. So that's another symplectic, another Lagrangian submanifold, and it's Hamiltonian isotopic to our original one. And Hamiltonian isotopy isn't supposed to change Hom in the Fukaya category. You're supposed to be the same object in the Fukaya category if you're Hamiltonian Lagrangian, Hamiltonian isotopic. All right. So what are intersection points now? An intersection point of the 0 section and the graph, that's a point where the function is 0. So our intersection point is points in my original manifold where df is 0. So critical points. Well, we already know one complex whose generators are given by critical points. That's the Morse complex. So if you construct homology or cohomology using Morse theory, you have a complex where your points are critical points of the Morse function. Morse function. And you compute your differential by counting gradient trajectories from one point to the other. So summing yeah, let me not write this out in detail, but you look at each pair of points, you look at how many gradient trajectories go from one to the other, and the differential of the class corresponding to a point is the sum over all the things it has gradient trajectories pointing to, weighted by the number of trajectories. All right, so Morse theory is pretty cool, but of course this really depended on one of my manifolds being the zero section and the other one being very close to it. So how do I get a complex like this that doesn't work that way, right? In general, there isn't going to be a function f. So how can I express the Morse function, the Morse complex, in a way that's sort of purely symplectic? The answer is pretty cool. It's based on work of Fleur. I'm going to kind of assume for simplicity that my symplectic form is exact, which of course happens on a cotangent bundle, and that it's also exact that when I take that one form and then restrict it to the Lagrangians, that one form becomes exact, right? If I restrict that one form to a Lagrangian, it's closed because the symplectic form restricted to the Lagrangian is zero. So I can impose the additional assumption that it's exact. And this, so one of the things you see in this sort of Fukaya category picture is you always start with a bunch of really restrictive assumptions, and then you kind of gradually remove them at the cost of making your life harder and harder. Okay. So I can use this to define an action functional on the set of paths that start on one Lagrangian and go to the other. So my path pi starts on L1, travels along for a while, ends on L2. And my action functional is just the difference between these values f1 at the start and end of my path and the integral of alpha pulled back to the path. And I should say, right, what is this doing in a way that the exactness helps me make easier? Why, if I had some reference path pi 0, what I would be calculating here is the integral of the symplectic form over the disk created by a homotopy from my path pi to pi 0. And life becomes more complicated if you don't have exactness, because then you have to worry about what disk are you using. Yeah. So let me not worry about that too much. We can think of this action function as a Morse function on the space of paths from L1 to L2. And try to compute the homology of that space of paths by looking at the Morse complex for this infinite dimensional space. Now, actually making sense of doing that is very hard, but if you kind of do it naively, then critical points end up being the constant path at an intersection point. So critical points correspond to intersection points. That's a good start. And then gradient flow lines end up being pseudo-holomorphic maps. So again, pseudo-holomorphic just means that I'm not assuming I have an honest complex structure. It just means holomorphic in the usual sense. So these are maps of the unit disk in C2 into my manifold M, such that this point, which I guess is I, goes to one intersection point, minus I goes to the other intersection point, and this cuts my unit circle into two portions. One of those should map into L1, the other one should map into L2. All right, so such a pseudo-holomorphic map connecting a fixed point, an intersection point P to an intersection point Q is a trajectory under the gradient of the function from P to Q. Whew. Are there any questions? This is not a bad thing to kind of ponder for a bit. So the picture you should have in mind, it's hard to draw this because I am not a great artist and it's not kind of an easy thing to draw in low dimensions, but that I have some Lagrangian L1, and then I have another Lagrangian L2. And of course, you should imagine these intersecting transversely, though I can't draw that. I have two intersection points, and I'm mapping in my disk in such a way that one side of the disk goes into one of the Lagrangians, the other side of the disk goes into the other Lagrangian. And I want to count all the ways of doing that. So this is, I mean, this is very hard, but we have techniques for doing it in at least some cases. So it's maybe not quite as insane as it sounds, even though it is very challenging. All right, so unfortunately, this space is big enough that it doesn't really make sense to say we're going to do Morse theory to compute its cohomology. But as sometimes happens in mathematics, we can just kind of ignore that issue and charge ahead. So we can think about the space of pseudo-holomorphic disks as above, and attached to each one of these, there's an invariant called the energy, which is just the integral of the pullback of the symplectic form along this disk. And I'll just note this has to be positive because of the compatibility of the symplectic form and the complex structure. Right, so by the compatibility, pulling back the symplectic form to the disks gives you a symplectic form on the disk compatible with the complex structure on the disk, and this energy is the volume of the disk with that metric. So it has to be positive. All right. Now it's easy to say those words, space of holomorphic disks doing this. It's a lot harder to actually like prove anything about that space. So this has, consumed a number of people's careers, getting all the details of this right. So there are really like a lot of difficulties. One is, well, you probably want to choose a generic almost complex structure. So if you choose your almost complex structure badly, then you might not get the right kind of transversality and get a well-behaved manifold where sort of integration works the way you expect. Another thing we're going to want is we're going to want to do a signed count of the number of these strips, right? So we want something that's invariant as we change the complex structure. And sometimes as we change the complex structure, we can get like new canceling pairs of strips can appear. So we have to do a signed count. So we have to make sure that the space of strips is orient. And this is possible in many cases, but you have to do some work. Often
why would we
sorry?
Why would we expect the number of strips to be finite in the generic case?
So
like, why wouldn't there be some higher dimensional moduli space of flows?
sometimes there will be.
Okay.
Um,
But if you set everything up nice, it ends up being finite.
well, a better way to say this is you only want to look at contributions to your differential from zero-dimensional moduli spaces. So if you think about the Morse complex, right? Let me see if I can actually draw an interesting case. If I draw a torus, right, and use height as a Morse function, I have 4 critical points, right? And this has Morse index 2, Morse index 1, Morse index 1, and Morse index 0, right? And so I only want contributions that go between critical points where the difference of the Morse index is 1, right? So if I start here at 2, well, almost every trajectory I can go out on will go down to here, right? There are only a finite number of trajectories that will land at these index 1 critical points. And so I only want to count those. So one thing I skipped over, because I think I correctly judged I would not have time, is how do I think about the Morse index of one of these intersection points? And this requires you to say like Maslov index, graded Lagrangians. So I'm happy to discuss it afterwards, but I think I just kind of don't have time to work it out. Yeah. So
this is like this is the Morse-Smale condition that guarantees that your flow generically goes only 1 index down or something. Isn't this related to the Morse-Smale condition? I remember this because when I was trying to learn Morse theory, this example confused me because it didn't quite work, but it turns out you need to like tilt the torus a little bit to get it to be Morse-Smale or something. Anyway, don't even bother.
I think we're getting too deep into the weeds.
Yeah, I'm just
So no, it's not always going to be zero-dimensional. You want to remember that the higher dimensional guys exist, but the contributions to the differential only come from the zero-dimensional guys, if I understand correctly. All right. But I mean, even if it were positive dimensional, we would want to integrate over it. So we would want an orientation. And I'll just note here, people quite often dodge this issue about orientation by working over Z mod 2. So like a very large amount of the literature of the Fukaya category in floor theory uses coefficients in Z mod 2, and it's exactly so they can avoid issues about orientations. Makes a lot of things easier. Another issue we have to worry about is compactness. So, this is, again, something I'm very far from expert in because it involves analytic stuff, and I don't like that. But every talk about floor theory I've ever gone to has involved some sort of question about like, oh, how do you prove that there isn't any bubbling? This is just like, there's certain of these questions you could like ask after every talk in a given field, and like, oh, what do you do about bubbling is like a question you could ask in every talk about floor theory, and that you probably will ask in every talk about floor theory. So the issue here is that if you're looking at how a pseudo-holomorphic map changes as you change the complex structure, you can end up with maps from the disk, a sequence of them converging to a map on some more complicated domain, where sort of part of your disk gets pinched off. So you can have sphere bubbling, which is like in the middle of your disk, a sphere gets pinched off. Or you can have disk bubbling, where on the edge of your disk, another disk gets pinched off. So you get these pictures like the disk I had before turns into this guy. So the danger is exactly that you might have a piece of this disk with its whole boundary in L1. So this would all be in L1, and then this would be in L2. Yeah, and the last thing that can happen is you might have a strip that kind of breaks in two, where before you were going from one critical point to another, and then it kind of snaps onto connecting to another critical point. So it stops being a map from a strip. It's a map from one strip and then another strip. And understanding all of this involves a lot of like serious work in PDEs. There's now this theory of polyfolds, which is supposed to make this all systematic, and but I don't know much more than the fact that it's supposed to make things systematic and nice. So I should say the sort of most problematic version of this is the disk bubbling. So, I'd mentioned we have this Morse complex. We're trying to generalize this to a Floer complex for two Lagrangians using these homomorphic strips. If you have disk bubbling, then you might just not get a complex. The differential might not square to zero. Exactness helps us avoid this, because if you think about this, I'm integrating the symplectic form over my disk. I'm supposed to get something positive. That can't happen if my symplectic form is exact by Stokes' theorem. So if I'm exact, I can't have a disk like this that bounds where all the boundary is in one Lagrangian. So part of the reason you quite often see the Fukaya category only discussed or initially discussed in the exact case is then you have a good explanation. When someone at the end of your talk goes, oh, well, why don't you have to worry about disk bubbling? You get to say, oh, well, my manifold is exact, so it's not an issue. All right, and if you do have disk bubbling, then you might have to sort of think harder about what kind of category you have. Allow yourself to have some differentials that don't square to zero. All right, well, assuming we can get around all of these analytical difficulties, which people have, then we can define a complex. And this is going to be over what's often called the Novokov ring. In this case, I'm thinking about C because for my own reasons, again, people would often want to do this over Z mod 2. But there's a polynomial variable in the picture where I'm allowed to raise that to arbitrary non-negative real numbers. All right. So I'm going to define a complex, often called CF, or people often add a star here, between the two Lagrangians. So the generators are points of intersection. Put that in a little bracket to show that we're thinking of the class associated to it. And the differential is I hit dp with my differential. I sum over Q such that this moduli space has dimension 0. So this is exactly what Matthew was talking about. I'm sort of skipping a bunch of stuff about Maslov indices here. The number of points in that space counted carefully and correctly, accounting for orientations and all that good stuff, or if you prefer, down over Z mod 2. T raised to this energy. So this is the space of disks with a fixed energy. And then the class of Q. So this defines my differential. As I mentioned, people quite often will skip this, but it's important for me because I want to get this homological mirror symmetry. I might instead want my Lagrangians to carry vector bundles with connection. And so instead of just saying I have the class of P, what I have is at each fixed point, I look at Hom between the fibers. So the story I had before that was if you put the trivial vector bundle on everything. And so Hom from the fiber of the trivial bundle, is just C. But I actually I don't usually think of it this way, but I think it's kind of nicer because it's a little more rigid. You sort of see what spaces things have to be maps between. And now the differential, well, I have to tell you what the differential of the map from the fiber of E1 to E2 at a point P is. And I'm integrating over the space of disks. I still have this term T raised to the energy. But the way I incorporate my map and my flat connections is I start at Q, I parallel transport using my connection up to P along one side of the disk. I apply this map F, and then I parallel transport down the other side of the disk. They're kind of like this because you see you're actually going around the disk. So whether you incorporate these E's or not, as long as you avoid this issue with disk bubbling, you will get a differential that squares to 0. And the homology of that differential is what people usually call Floer homology. Are there any questions? Okay, so we can use this to define a category whose objects are Lagrangians equipped with a vector bundle with flat connection. And the product is based on the space of mapping in disks, where instead of just cutting up the boundary into 2 pieces, I cut up the boundary into 3 pieces and require one go to the Lagrangian L1. This guy, choose a color.
Product, you
this
mean?
Goes to Lagrangian L1.
You mean
this
monoidal
goes
product?
To Lagrangian L2. This goes. Sorry.
You mean monoidal
No,
product, or as in like?
No, I mean composition of morphisms in the category.
Oh, sorry.
Right. If I'm so, if I'm going to define a category, I have to give you a product where I start with one of these homology classes going from L1 to L2, one of these going from L2 to L3, and then I need one going from L1 to L3, right? So if I'm going to have composition, I have to have 3 things in the picture. So I have an F that goes from E1, E2 at a point P. I have a G that goes from E2 to E3 at a point Q, right? So these define chains in this Floer complex. And I have to tell you what the product of 2 of those is. And the kind of cool thing is it's exactly the same picture. I may have switched the direction I'm going around my disk, but I think this is okay. I start at one point. So I'm looking at disks that map in that send 1 point on the boundary to P, 1 point on the boundary to Q, and then a 3rd point on the boundary to some other intersection point between L1 and L3, which is R. And the sort of contribution of each disk is I start at R, I parallel transpoint to this point P, I apply F. Now I'm on L2, I transport along L2 to get to Q, I apply my G, I parallel transport along L3 to get to R. And so going around that circle gives me Hom from E1 at R. So this result here goes from E1 at R to E3 at R. So it's defining an element of the a chain for the Floer complex going from L1 to L3. And this defines for me composition. This is what I need to actually have a category. All right. So probably most of you have not been kind of inducted into the DG creed. But usually actually you should be very dissatisfied if somebody tells you like, oh, I'm going to define for you a category and the morphism spaces are going to be this homology. Because you're losing information by taking homology, you should be remembering the whole chain complex, trying to think of the whole chain complex as the hom space. And that's what we
understand what the mapping space is, that this is like an invariant of the homotopy type of, right?
Sorry, say that again?
Never mind.
Yeah, I mean, if you thought about algebraic topology, like remembering the chain complex of a manifold is more information than just the homology. So taking homology kind of loses information in a bad way, in particular to make this theorem relating to coherent sheaves work really properly. Taking this homology is a bad thing to do, so it would be better to remember the whole complex. And it would be nice if I could say that this was a DG algebra. That's not actually quite right. So this product that I define using these integrals, it's not associative on the level of chains. It doesn't define a DG algebra structure. I need kind of additional homotopies to make the associativity work out. But the kind of cool thing is those actually can be found in exactly the same way by taking a disk and cutting its boundary up into 4 pieces instead of 3. So, in this case, I'll be looking at morphisms going from L1 to L2 to L3 to L4. And then there's going to be 2 different ways to bracket these, right? I can do this composition first or this composition first. And I won't get the same answer. I'll only get the same answer up to homotopy. And the homotopy that relates them is going to come from an integral over spaces of disks like this. And it turns out you need sort of to do this with more and more and more division points on your disk. What you get is something that's called an A infinity category. So the Fukaya category is one of the kind of most interesting examples where you really need this full A infinity structure to describe fully what's going on. That's its own story, which I'm not going to be able to explain in the 10 minutes left in the talk, but that sort of captures the information that you would lose passing to just homology. All right, so this category, this is what Kontsevich predicts will be the A-side analog of coherent sheaves. That the coherent sheaves on the mirror will be the same as this Fukaya category on your original manifold. And one ends up with sort of a nice explanation of what's going on in SYZ. So remember in SYZ, we had this base. We had M mapping here, and M dual mapping here and M mapping here. And if we had a point in here, well, we can turn that into pi inverse of pi check applied to that guy, which is a Lagrangian. With a corresponding U1 connection. So a corresponding flat line bundle. on a Lagrangian in here. And so the connection between homological mirror symmetry and SYZ is that this equivalence should send the object, the skyscraper sheaf on P, to, well, this Lagrangian with the corresponding flat line bundle. And we had done one calculation of, not done, but I told you that I could do this calculation of X to the skyscraper sheaf with itself and get this exterior algebra. Well, that exterior algebra, that's also the homology of this torus. And it turns out the homology of that torus is the self X of that object in the Fukaya category. So you can see that these objects you get in the Fukaya category from SYZ behave homologically like the skyscraper sheaves on points on the B side. The other part that I didn't say here is, of course, if you take X of the skyscraper sheaves at two different points, then that would be 0. And the same is true for HF of.
Are you writing things? Because I don't think we can see you writing, just FYI.
Yeah, I think there's some delay.
Oh.
Yeah, I'm not sure what's going on here. I'll catch up eventually. It's risky, but I can stop my share and try restarting it. That was not what I wanted to do. Okay, good. So if I have the Hegarde-Floer homology relating two of these guys, so either two different U1 connections on the same torus fiber or two different torus fibers, then I also get trivial Hegarde-Floer homology. So this is kind of the first calculation that tells you why homological mirror symmetry should hold if you believe SYZ, or why SYZ should hold if you believe homological mirror symmetry. All right, are there any questions?
Is there any connection between this and geometric quantization? Because you're talking about Lagrangians with a flat line bundle over them. This sort of reminds me of because in geometric quantization you get a line bundle over your manifold, and then over any Lagrangian this restricts to become flat. And yeah, I don't know.
I see the connection you're making. I think the answer is, if there's a connection, it's a very, very abstract and tenuous one.
Okay.
I don't think there's a like, oh yeah, they're the same thing because of this. I mean, I think you actually can interpret a lot of this quantum field theory in terms of geometric quantization, but it's quite a bit more abstract. You have to start saying things about like shifted symplectic structures and.
Yeah, I don't know. And then also when you were talking about the exactness condition and these functions F, like those are like the phase functions in geometric quantization. So it's like, I don't know. It's just something something I vaguely understand.
I don't see the connection right now. I mean, especially because, like I'm not taking sections of the bundle.
Right. Right. Well, no, it's just a line bundle with connections. Like, doesn't mean that it has anything to do with. I was like hoping there was some way I could connect this to something that I understand a little better, just because I've been studying it recently. But yeah, it's okay. Just thought I'd ask.
Right. I mean, I think like physicists would tell you something like, this story is something about the 2D sigma model into your manifold, and geometric quantization is about like a 1D sigma model into your manifold.
Sorry, what's a sigma model again?
It means a theory that's based on mapping, looking at all the different maps of some fixed world sheet into your manifold. So I think that kind of the geometric quantization story like has to do with mapping one manifolds in, whereas this is a string theory story. It has to do with mapping two manifolds in. Hopefully that isn't too wrong. I suspect also physicists would say like there's supersymmetry in the picture here, right? So like the geometric quantization is about usual quantum mechanics. Like if you turn it into supersymmetric quantum mechanics, like your Hilbert space will become just the homology of your manifold. Somehow like adding in the supersymmetry cuts out a bunch of the geometry and leaves you with something topological.
Wait, can you explain that a little more?
No.
Okay.
Okay. Not in the time we have here. And I'm not sure I want to try, but
okay, fair enough.
I suspect like that's sort of if you want to kind of phrase like why is it a different thing? I mean, all of this stuff we're talking about now, this is all about, I mean, once you've done the A twist or the B twist, this is about topological field theories. So there's like no interesting time evolution, which is like very different from like the usual old quantum mechanics you do on in geometric quantization. At the risk of getting myself into more trouble, I think I thought of the sort of very glib answer to your question about the supersymmetry thing, which is like the super part means that you go from functions to K forms of all degrees. You're adding in a fermionic part that gives you these higher degree K forms. And then the supersymmetry is like adding in the de Rham differential and taking homology with respect to that. Yeah, so I suspect there are things you could read that would explain it better than I could explain it, but that's sort of what, very roughly how you're going from functions to homology.
I'll have to look into that.
All right. Any other questions?
You're teaching a class in the fall?
That is true.
What's the title of the class?
I would want to look it up because I made it a little more of a mouthful than I should have, but it's about category O.
Category O?
Yes. It's about the representation theory of Lie algebras. So category O is a particularly nice category of representations of Lie algebras. At least very anecdotally, I had heard that the name comes from when they first found it, they said, "Oh, that's the category we should be studying."
Are you kidding? Oh my god.
I maybe I may be.
Mathematicians need to do better.
I was told that story semi-seriously, but it may well not be true.
They need to stop like giving one letter names to things, because it's hard to Google that stuff, you know, like I don't know.
Yeah.
This is like but
If you
that's
Google
funny.
BGG category O, you can get more interesting.
Yeah.
If
Yeah,
you-
the thing that's actually very annoying, right, is they use the script O, which is also the symbol they use for the structure sheet. That's the really annoying thing about that name.
and they have nothing to do with each other.
Well,
I think they're related.
some people would want to discuss both of them in the same paper, making it very awkward.
That's terrible.
Yes, I agree. It is terrible.
And I don't like how to write them. I think this really like influences my choice of interest. I don't like writing that script O. Like my script O's just look kind of ugly.
Well, I mean, like we wrote a paper where just like to avoid this confusion, we started using a different symbol for the structure sheet, because it was just like too confusing if you write a paper about category O and you have to talk about the structure sheet. I mean, there's like a connection between them in that, like, if you look at the structure sheet on a flag manifold, like you get a finite, its sections are a finite dimensional representation, which lies in category O. Certainly you would have cause to mention both of them in the same paper. I would have cause, maybe not everyone would.